Dear students, in this class, let us derive the expressions for work done during an isothermal process and work done during an adiabatic process. In the last class, I had explained the different types of process taking place in a thermodynamical system. The different types of process are isothermal, adiabatic, isobaric, isochoric, and cyclic process. Now, let us consider the isothermal process. What a process is? The process in a thermodynamic system is nothing but change in the state of the system or change in the coordinates of the system. The coordinates of the system, thermodynamic system, are pressure, volume, temperature, and entropy. Now, let us consider the isothermal process. What is an isothermal process? The process taking place in a thermodynamic system under constant temperature. The change in pressure and volume takes place by maintaining the temperature constant. Such a process is called an isothermal process. So here, let us consider one such isothermal process. For this, consider 1 mole of an ideal gas in a cylinder, and the cylinder here, it is fitted with a piston, frictionless piston. Let the walls of the cylinder be the perfect conductor of heat. Let the walls of the cylinder be the perfect conductor of heat. The cylinder contains the ideal gas. Suppose the piston is pulled slowly outside. Now, the gas in the cylinder expands slowly. The slow expansion or slow compression of the gas is the example for an isothermal process. So here we consider the slow expansion of the gas. As gas expands, the work is done by the gas now. During expansion, the work is done by the gas. How the gas works done? By using its own internal energy. As a result, temperature decreases. As the gas consumes or uses its own internal energy, decrease in internal energy takes place. Decrease in internal energy means decrease in temperature. So here, during expansion, temperature decreases. But what happens here? The process isothermal means the temperature should be maintained constant. How the temperature is maintained constant here? Because of thermal communication between the system and the surrounding. As the walls of the cylinder are the perfect conductors of heat, heat flows from the surrounding to the system, thereby maintaining the temperature constant. Thus, expansion of the gas takes place under constant temperature. So, during expansion, what happens to pressure? Pressure decreases and volume increases and temperature here remains constant. And this variation is represented in the PV diagram like this. PV diagram here, this curve indicates the slow expansion of the gas. Volume goes on increasing, pressure goes on decreasing, maintaining the temperature constant. Now consider one state of the system, one state of the gas here. Let P1 and V1 be the pressure and volume of the gas before expansion, initial state. Let P2 and V2 the pressure and volume after expansion. Now here, if you consider a small change in volume, say dV at a pressure P, then the work done during this expansion, during this change in volume given by P dV. And that work done is very small. For a small change in volume, we denote it as dW. dW is P dV. Here in our case, the volume changes from V1 to V2. For this change in volume from V1 to V2, the total work done, W, is given by integration of this expression between the limits V1 and V2. That is, integration of P dV between V1 and V2. The gas is the ideal gas. So, ideal gas equation, PV equal to RT whole square. From this, we can write P as RT by V. Now, substitute in this equation P as RT by V. So, we get W as integration of RT by V dV between the limits V1 and V2. Now integrate. See here RT constant. Keep it outside. Integrate 1 by V. Integration of 1 by V is ln V or log V with base E. Limits V1, V2. Apply the limits. You get this. And you know that log A minus log base log A by B. So that this one becomes W equal to RT log V2 by V1 with base E. Convert this one into log with base 10. So that how do you convert? By multiplying the constant 2.303. So we get the total work done as 2.303 RT log V2 by V1 log with base 10. Here this one can also be written as ln. This way also you can indicate ln is log with Neperian base E. And the process is isothermal. That means the equation for an isothermal process is PV is a constant. We have seen this one in the last class. PV is a constant for an isothermal process. PV constant means P1 V1 is a constant, P2 V2 also a constant. Therefore, P1 V1 equal to P2 V2. Both will have the same constant K. P1 V1 equal to K, P2 V2 equal to K. So that P1 V1 is P2 V2. From this, we get V2 by V1 as P1 by P2. So, this expression can also be written in this form in terms of pressure. And these are the expressions for work done during an isothermal process. Now, consider an adiabatic process. What's an adiabatic process? The change in pressure and volume taking place under thermal isolation. The pressure and volume of the given gas or the given system changes under the condition thermal isolation from the surrounding. The system is completely isolated so that the temperature in the system is not maintained constant. As the temperature changes, it remains as it is. Pressure, volume, temperature all will change in this case in the adiabatic process. Again here, consider 1 mole of an ideal gas in a cylinder. But here the walls of the cylinder are the perfect insulators of it. They do not conduct heat. The walls are non-conducting, perfect non-conductors of heat. Cylinder is fitted with a piston, which is also a non-conducting one. So, here no contact or communication between the system and the surrounding. How the process becomes adiabatic? In this case, when the piston is pulled suddenly outside, the expansion of the gas takes place suddenly. There will be sudden expansion of the gas. This is the example for adiabatic process. Similarly, suppose the piston is pushed down suddenly. Piston pushed down suddenly. See, just remember this diagram. A piston here. The cylinder is, this is the cylinder, not the piston, This is a cylinder fitted with a piston. This is a piston. Gas, this cylinder is filled with the gas. Now, sudden pushing it down. Nothing but compression of the gas, sudden compression of the gas. Sudden moving it outside. It is sudden expansion of the gas. Examples for an adiabatic process. Here, in this case, let the piston be pulled outside suddenly. The gas expands suddenly. So now, what happens? The work is done by the gas by using its own internal energy so that temperature decreases. Since the walls are the perfect insulators, no connection between the surrounding and the system. So, what happens? Temperature remains as it is. It decreases only. It is not maintained constant. So, here, what happens in this process? Volume increases, pressure decreases, temperature also decreases. Let the change in the temperature be dt. That the temperature changes by an amount, say dt. P1 V1, pressure and volume before expansion. P2 V2, pressure and volume after expansion. Now, the small amount of work done for a change in volume dV given by integration of dW between the limits V1, V2, nothing but integration of P dV between V1 and V2. For the adiabatic process, the equation is P V power gamma is a constant, say K. This is the equation for an adiabatic process. We had derived this one in the previous class. From this, P is K by V power gamma. Substitute here. We get W as K integration of dV by V power gamma between the limits V1, V2. That is K constant. Take this one to the numerator, V power minus gamma. Now integrate this. You know how to integrate. Integration of V power minus gamma is V power minus gamma plus 1 by minus gamma plus 1, V1, V2 limits. Apply the limits here. See here, K is taken inside. And now apply the limits. You get W as 1 over 1 minus gamma. See, this is minus gamma plus 1, 1 minus gamma. So, K by V2 power gamma minus 1 minus K by V1 power gamma minus 1. And for the adiabatic process, P V power gamma constant. And since this product is a constant, this is true for any pressure and any volume. That is, P1 V1 power gamma is a K. P2 V2 power gamma is also K, so that P1 V1 power gamma equal to P2 V2 power gamma, nothing but K. Now here in this equation, let us take K as, here first term, let K be P2 V2 power gamma, and take this K as P1 V1 power gamma. Simplify, you get this. See here, V2 gamma minus 1, you take this to the numerator, becomes minus gamma plus 1. So minus gamma 0, remaining is V2 power 1, that is V2. So we get this. And ideal gas, PV is RT. And this is true for any pressure, volume and temperature. So that P1 V1 should be equal to RT1, P2 V2 should be equal to RT2. Substitute these two in this equation, you get W as 1 over 1 minus gamma RT2 minus RT1. Or from this, W is R by 1 minus gamma into T2 minus D1. And this is the expression for work done during an adiabatic process. With this, I stop here.